Welcome, I'm Nick. In this video, I will solve Griffiths problem 6.29 as it appears in the third edition of the book Introduction to Quantum Mechanics. This problem asks us to prove Kramer's relation, which is what appears right here. And this relation, what it does, it relates the different powers of the expectation value of R for the hydrogen atom. So for example, here we have R to the S, R to the S minus 1, and R to the S minus 2. And why is this useful? Because we have in a previous problem, in the one I think it's like well, I don't remember the number actually, but it's the one where we prove the Feynman-Hellman theorem. There we found the expectation value for 1 over R squared and for 1 over R. And the thing is that, for example, now that we're working towards the spin-orbit coupling correction to the hydrogen atom, well, there we need the expectation value of 1 over R cubed, but we don't have that. And the thing is that if we can prove this, that means that we can then use it. And here, for example, if we had, well, if we want to go to S to the or R to the minus 3, we would have to take S equal to 1, and we will have a formula here that relates R to the minus 3, which we don't know, to R to the to the minus 2, which we do know, and R to the minus 1, which we also know. So basically, this formula or this relation would help us find the expectation value of 1 over R cubed, which we will need. And well, in principle, of course, you can then go forward to R to the 4th or R to the 5th or whatever you want. But for now, our main goal is to find R cubed, well, 1 over R cubed, but that is for a later video. Okay, so how do we go about proving this? Well, let us think about the expectation values, right? So if we have the expectation value of R to the S, what this basically means is that this is the integral of U. What is U? U is this radial function, right? Remember, in the case of the hydrogen atom, we are integrating from 0 to infinity of this radial function U, which, if I remember correctly, I think it was like R times R. I'm doing this from memory, so I might be wrong. Maybe it was divided by R, but I think it is R times R. But either way, that's what this U function was. It depends on R. And then it will be times R to the S, UR. And of course, this is complex conjugate, but since it's a real function, it doesn't really matter. We don't really need to include it. So yeah, this is what the expectation value is. And the thing is, if we want to relate this somehow to R to the S minus 1, R to the S minus 2, then the formula for that, whoops, I think I pressed the wrong thing. All right. The formula for that would actually be quite similar. So R to the S minus 1 would be basically the same thing, but of course with S minus 1. And in the case for S minus 2, it would be the same, but with R to the S minus 2. So the question is, how could we relate all of these quantities? And the answer to that is going to be to think of this a bit differently. So now you might remember what we had in the hydrogen atom, okay? So we have R to the S, and we know that we will have something when we do the expectation value, right? Some expectation value. We have the integral, and now we would like to have like a bigger equation that contains different powers of R to the S, R to the S minus 1, R to the S minus 2. And that is why, in a clever trick that might be hard to come up with, I admit, but it is the logic here. We know, I'm gonna leave this for just a few seconds, we know that U prime prime, now this is an equation that comes from the hydrogen atom that we saw in the first course in quantum mechanics. Now we know that U prime prime is L plus 1 divided by R squared minus 2AR plus 1 over N squared A squared U. All right, so that was the radial differential equation that we solved in quantum mechanics 1. And if you see this, U prime prime, what does it include? It has 1 over R squared, which is basically R to the minus 2. So if we multiply this by what we have up here, we will get this term times this is r to the s minus 2. When we multiply by this, we get r to the s minus 1. And when we multiply by this, we get r to the s and, minus 0. And that would actually give us what we want. So what this tells us is that one way to solve this would be, actually maybe I shouldn't write it like this, now that we are going to go more general. The expression that we have to start off with is going to be u r to the s u prime prime dr. Okay, so that's basically what we now have to solve, and hopefully that will give us our relation that we can use. Okay, so that is our starting point. Okay, all of this was just us trying to find our starting point. What next? Well, we want to solve this, so let's begin by plugging in u prime prime into that integral. So we will have integral of u r to the s times, and then we have l plus 1 r squared, and then we get, well, minus 2ar plus 1 n squared a squared u dr. Okay, so let's now multiply through in the next page. And oops, I did not intend to do that, but it's fine. All right, now let's multiply through. So we will get 3 integrals. So the first one is going to be, well, maybe we can pull out the constant outside. So l plus 1, and then we get integral u r to the s minus 2 u dr, right? That's this first part. So this times this, and of course, don't forget about the u dr. All right, second part, it's going to be minus 2 over integral of u r to the s minus 1 u dr. And finally, we have plus 1 over n squared a squared integral. This is going to be u r to the s u dr. And well, now if we take a look at this right here is simply the expectation value of r to the s minus 2. It's literally the definition of it. Maybe you can write it with the complex conjugate if it makes it look a bit more intuitive to you. And this right here is going to be r to the s minus 1. And this right here is going to be the expectation value of r to the s. So that means that the expression that we had, so this integral of u r to the s u prime prime dr is going to be l plus 1, expectation value of r to the s minus 2, minus 2 over a, expectation value of r s minus 1, plus 1 over n squared a squared r to the s. All right, so maybe let's get rid of this. This is what we have now. And the right-hand side is looking quite good. I mean, it's got L, N, A, and all of those are constant, so there's no problem in them being there. And then we have the 3 expectation values that we actually want to end up with. So that's already looking quite good. The problem is that the left-hand side, this right here, that doesn't really mean anything, right? We don't really know what that is. We only know that it's equal to the right-hand side. So now we have to find some way to, work on the left-hand side in a way that will give us some relation. So let's now try to do it. Oh, I do not have my select button working. Okay. There. All right. So let's now put this maybe in a box so I don't forget about where it is. And then we will work on solving the left-hand side. All right, so this right there. Well, one way to go about it, and it's probably the easiest one, is to use integration by parts. Why? Because, well, we have a part there, the u prime prime, which is, the derivative of something. So if we use integration by parts, we might, get along, maybe go somewhere. So let's try that. So if you're going to use integration by parts here, then maybe let's call this I, by the way, or let's call it ILHS, so the integral left-hand side. Okay, so In our integration by parts, let's call this right here. So let's call W is going to be, I don't want to use U, of course, because we already used that. So W is going to be U times R over S, and dV is going to be U prime prime dr, right? Because of course we want the dV part to be the one that we can integrate the easiest. So of course we don't want to allow the RS or the U to be on that side. It would make everything much more complicated. So, well, what would the W be? Well, this would be, this is, you have to apply the product rule here. So it's going to be U prime times R to the S plus U times R to the S minus 1 times S. All right, and V would, and of course dr, don't forget about that, dr. And V would be U prime. All right, so now the integral, the ILHS, this would be this times this. Maybe let's change the color. So V dr, right, evaluated, W times V, evaluated at the endpoints. So that would be U R to the S times U prime, evaluated at the endpoints, which are 0 and infinity. However, how did we define this radial function back then, right? In the first part of in the first course in quantum mechanics? Well, we defined it in such a way that it goes to 0 both at infinity and at 0. So that means that both of these endpoints, when we evaluate U at both of these endpoints, it's going to be 0. So this entire thing right here is 0. So goodbye to U. So that leaves us at only the second part. So this is going to be minus this times this. So that's going to be, oh, and the integral, of course, the integral of U prime RS. I'm actually going to separate both integrals now. U prime dr minus integral of S U R S to the minus 1 U prime dr. So these are our two integrals, and maybe let's write this S right here on the outside. So minus S right there. Okay, and there's actually another thing that we can do. We can write this as U prime squared, right? We can commute these functions without any sort of problems. R to the S, it's simply a constant, basically. I mean, it's not a constant, but it's just a scalar, so you can move it around. There's nothing problematic there. Okay, so now we have two more integrals that we need to solve. Maybe let's call them I1, and this right here is going to be I2. Now, please be very careful, because this will get a bit messy. There's going to be a lot of algebra here, a lot of minus signs floating around. So please, be very, very methodic, so you don't make any unnecessary mistakes. So now let's begin solving I1. Well, it doesn't really matter which one you want to solve first, of course, but whatever. So I1, this is integral of U prime squared dr. And now I want to make a quick comment, because in principle, what you could do to solve this is that instead of writing it like this, you write it as the integral of U prime, oh, I'm missing my R to the S, yes, R to the S U prime dr. And you could say, all right, W is going to be U prime R to the S dW. This is going to be, well, the derivative of this, so it's going to be U prime prime, and then times R to the S plus U prime times S R to the S minus 1, and then our dV would be U prime dr, and then V is going to be U. But the thing is, when we do this, so the first part, this product is of course going to be 0 again, because we have a U that's going to be evaluated at the endpoints, which are going to be 0. So we get that I1 would be minus integral of U prime prime RS, and then we get the, whoops, I missed the U, UDR, minus integral of U prime S R to the S minus 1 U dr. And we could continue going, but the thing is that we are going to get to a recursive relation that is not really going to be useful. So if we go down this path, we're not really going to get to where we want to go, right? And I actually tried this part first, and then I noticed that I got to a dead end. So that's when you have to then notice that you just have to go back and try something else. That's why we will stick to what we wrote down here, which I'll write a bit more clearly. Right, so I just wanted to make that clear. If you're not sure, by all means, go ahead and try it out. There's nothing bad with it. There's nothing wrong with that. But the way that's actually going to lead to a result is going to be this one. So what we're going to do here is we're going to say, all right, so W is going to be U prime squared, and dV is going to be R to the S dr. All right, so what's the W? It's going to be 2 U prime prime. And then we have V, which is going to be R to the S plus 1 divided by S plus 1. Okay, so what's the integral this time? So I1 is going to be this times this right here. What's that? That's going to be U prime squared times R S plus 1 evaluated once again at our endpoints, which we know is going to be a big no-no. This is going to be 0 once again. So we are left again with only the second part, which is going to be minus 2 U prime, well, all of this inside an integral, of course, times R to the S plus 1 over S plus 1. Okay, so now we have this other integral, which doesn't really seem to have made much progress, but we actually did. All right, so let's go to a new page so we can work on this integral. Okay, so how would we solve this? The thing is, we have once again a U prime prime. So if we plug U prime prime here, we're going to get a bunch of things that are going to be of the form integral of U prime R to some power times U dr. Right, because we are going to have this U prime here, then we are going to have U prime prime, which is basically something which is like L plus 1 divided by R squared. So we are going to get R to the S minus 1 here. Then we'll have another term that is similar, but with R to the S, and then another one with R to the S minus 1, I think. I did it in my head, so maybe I got a bit of that wrong, but the idea of that is that this is going to be the shape or the form of every single term. So we are going to have to solve integrals of this form. And that's why it's good to take a step back and just get a general formula for this, so we don't have to calculate the same thing over and over again. But just to ensure that you guys understood what I mean, I'm going to actually plug this in first, just to be safe. So I'm gonna rewrite what U prime prime was. So U prime prime, I think it can fit, right? U prime prime, this is L plus 1, and I already forgot about it. Where did I write it down? Here. R squared, I have it here actually, so maybe let's just use it. Minus 2 AR and plus 1 over N squared, A squared, and all of this times U. Okay, so that's what we have to plug into the integral now. So what is that going to be? It's going to be, well, I1 is minus integral of 2U prime times L plus 1 R squared minus 2AR plus 1 N squared A squared times U times RS plus 1 S plus 1 dr. Okay, so what will this give us? So this will give us minus, maybe let's pull out the 2 in front as well, then integral of, maybe I'm going to separate this. So the first integral will have L plus 1, which I can actually, I think, pull out of this, L plus 1, and then we get integral of what? We have U prime, and then we have R to the S plus 1. Actually, I can pull out the, I'm going to do it here. So I can pull out the S plus 1, by the way. This right here, I can just pull it out. It's going to make things easier. So then we have this R to the S plus 1 divided by R squared, which is R to the S minus 1. Okay, what comes next? So next, we have this u that is lingering around there, and then dr. Okay, this is this integral. Then comes the next one, which is going to be minus 2 over a, minus 2 over a, and this is now multiplied by, well, this is whoops, that my pen lagged, and this is now u prime, and then we have r to the s, because this 1 cancels out with this r, and then we have u dr, and then finally we have plus 1 over n squared a squared integral of u prime, and then we have r to the s plus 1 u dr. Okay, I'm gonna just quickly make sure that I didn't make any dumb mistake, because that would be very annoying. So minus 2 goes out, so does s plus 1. Then we have l plus 1, which goes multiplying this integral, which has u prime r to the s minus 1, u dr minus 2a, u prime r to the s, u dr, 1 and an a. Yeah, I think we got it. Yes. Okay, great. So as we can see here, we got what I mentioned before. We have something of the form u prime r to the k u, u prime r to the k u, u prime r to the k u. So it is worth it to, instead of solving this integral 3 times, let's go for just a general formula, and then we will just plug it in, and that will help us save quite a bit of time. Because, spoiler alert, but we will actually encounter an integral of the same form later on. So it is really, really useful to do it beforehand. So let's do that now. So this integral, I don't know, maybe let's call it integral common, I don't know. This common integral that we will find is u prime r to some power k and u dr. So let's solve it the way we have been solving so far. So let's call w is going to be u prime times, let's see, should we use this? We should probably do it the other way around, I would say. So u r k, and then we take dv to be u prime dr, right? Let's see if this works. So what would this mean? This would mean that this would be u prime r k and plus u times k times r to the k minus 1, and this right here would be u. Okay, so here once again, the first part of this integral, the one that is this product, so v times w, that would simply be 0 because of the boundaries going to 0, and we are only left with the second integral, the one that, the only integral there actually. So we have minus integral of u prime r k u plus u squared k r k minus 1 dr. Alright, so this one is of the same shape. Yeah, take a look at this. So this one right here is the same that we had before, but now we have this thing right here. Is this better, you might think? Well, let me maybe write all of this together, because the I common is this right there. So it's going to be, maybe let's change colors. So it's going to be integral of u prime r to the k power u dr. This is equal to minus that same integral r k u dr. And now this right there, maybe let's write it differently. It's going to be minus integral of, maybe let's put a k in front, of u r to the k minus 1 u dr. What is this? This is the expectation value, right? This is an expectation value. It's simply the expectation value of r to the k minus 1. Nice. And since this is the same as that, actually let me go to a new page. I don't want to make this too chaotic. Let's put it there. So let's add this to the left-hand side. So we get 2 times this integral u dr. This is equal to minus k times the expectation value of r to the k minus 1. And now we can simply divide by 2. And we have solved or found a general formula for this integral. Amazing. So this integral is minus k over 2 times the expectation value of r to the k minus 1. Let's now use that. So let's go back to our I1, where we had 3 instances where an integral of this form appeared. Maybe let's go to a new page. So this was our I1. I'm going to be very clear in my notation and what everything is, because it's going to get messy. Okay, so let's plug our results in. So this I1, this is going to be minus 2 over s plus 1 times L plus 1 times, and now we use the formula instead of this. What was the formula? I'm gonna put it here as a reminder, maybe with a different color. So the formula was that the integral of u prime r to the k u dr, this is minus k over 2 expectation value of r to the k minus 1. Okay, so if k is s minus 1, then this formula tells us that this right here is minus s minus 1 divided by 2 times the expectation value of r to the s minus 2. Great. Now, what comes next? Then we have this other integral. So that's going to be minus 2 over a. And once again, this time k is simply going to be s. So we get minus s over 2 expectation value of r s minus 1. All right. And the final one is going to be plus 1 over n squared a squared. I just noticed there's no parentheses here. Doesn't matter, but and then it's minus, what is k? K is s plus 1. So we get minus s plus 1 divided by n, actually, well, we already used that actually, divided by 2, and expectation value of r to the, instead of s plus 1, it's going to be s, right? Because we subtract 1, so it's s plus 1 minus 1. And parentheses here and here. Okay, so this is integral number 1. Phew, all right, let's maybe simplify this algebraically just a bit more. So maybe actually I'm gonna get rid of this parentheses again, it's in the way. I'm gonna move this up just a bit so I have some more room down here. So let's try to, put everything together a bit more concisely. So we can multiply through by minus 2 and by s plus 1. So we get L plus 1 times s minus 1 divided by s plus 1. The minus sign here cancelled this minus sign, and the 2 cancelled this 2. And then we get r to the s minus 2. Okay, then we have this. We have minus minus, so we get a plus. This 2 cancels out this 2. And we are left with a minus sign from the outside times 2s divided by a times s plus 1 and times the expectation value of r to the s minus 1. Let me double check. So these cancelled out. We get a minus sign, 2s, a, s plus 1, and the expectation value. All right, seems good. And finally here we have this minus sign here, which will turn into a plus because of that. This 2 will be cancelled by this one. All right, so we get plus 1 over n squared a squared. Maybe instead of 1 over, I can write s plus 1. Actually, the s plus 1 cancels out, right? So this s plus 1 will cancel out with this one. So we don't have to write it down at all. So let me now double check. So of course we're missing this. So minus cancels out, 2 cancels out, s plus 1 cancels out. All right, seems good. Amazing. So this is integral number 1. Now let me put it in like a huge box because I don't want to forget where this result is. Okay, so this is integral number 1. Let's go back a little bit. Okay, so what we now need to solve is this integral number 2. Maybe let's go to a new page here. So integral number 2, I2 was, I already forgot. It's u r to the s minus 1 u prime dr. But the thing is, this is once again an integral of the same form of u prime r to the k u dr. Sure, the u and u prime are switched, but that doesn't make any difference, right? You can just move them around. There's no problem there. So here we are simply going to use our formula. So that means it's going to be minus k, which in this case is s minus 1, divided by 2 times the expectation value of r to the k minus 1. And since the k is s minus 1, it's going to be s minus 2. So there we go. We already have a result for I2. Amazing. So let's now put everything together. Where was our formula here? So we have to put it into this integral right here. So let me copy it, go to a new page, and just plug all of our results in. Does it fit? Yeah. Okay, so I1, we already found the result. Let me see if I can find it. Good question. I think it's somewhere over here. Yeah, here it is. This was our result I1. I think I dragged a few additional things, but I'll fix it. Yeah, we don't really need this. All right. So this right here is I1. And what is I2? We also found it quite recently. It's this right here. So this is I2. All right, so let's plug I1 and I2 into our ILHS, right? The left-hand side. Okay, so let's take a breather. Let's take a breather and let's go for it. So the integral, or what we called ILHS, is minus I1. So minus this beast. Actually, I'm just gonna, maybe I'm gonna try to write it down a bit more compactly. So it's gonna be minus L plus 1, S minus 1, S plus 1, expectation value R to the S minus 2, minus 2S over A, S plus 1, expectation value of R, S minus 1, plus 1 over N squared A squared, R to the S. And this is, and actually, whoa, we have to be careful with the signs here. Whoop, careful. Because it's minus this thing. So it's minus all of this, right? So let's now just put a minus sign through. So the first one will be negative, this one will be positive, and the last one will be negative. So very, very careful that we don't forget about that minus sign. Okay, now we have minus I2. I will use a different color. So minus S times, right? There's an S right here, don't forget about it. Minus S times I2. So minus S, S minus 1. And by the way, there is a minus sign here. So this will actually turn into a plus. Divided by 2, R to the S minus 2. Okay, so this is our ILHS. Well, where did this go originally? Let's go back and find out. I'll be honest, I'm not sure where I put it. Where did we define it? There it is. So ILHS, maybe let me get rid of this so I can use this space. ILHS was precisely the left-hand side of our original expression, right? At the very beginning of the problem, we found this expression by simply plugging u prime prime into this integral, and then we went ahead and integrated this by parts. So we found the left-hand side and the right-hand side. So we now have to put them together. So this is where you had the left-hand side. Let's just copy it and paste it here. So this, now these two things have to be equal, right? So maybe let's move this a little bit. So yeah, they are equal. This is equal to this. Whoop. All right. And this is already our final expression. Now all we have to do is use some algebra to, simplify this a little bit, to find some way to write this down in a compact manner. But in principle, we are already done. This is already a relation between the different powers of the expectation values of R for the hydrogen atom. All right. So how exactly do we do this? Well, let's start by putting everything to one side. Okay, so maybe let's add to both sides of the equation what we have down here. So basically, subtract or add depending on the sign. So the way I'm going to do this is I'm just going to do it right away. So I'm going to say, okay, let's add it. So this right here would be plus. This right here will be minus. Then we have a plus here and a minus here. And of course, all of this has to be equal to 0. Right? 0 equal to all of this. Great. Now let's factor out our different expectation values. So let's go for expectation value of R to the S minus 2. And what is multiplying this expectation value? Well, we have here L plus 1, S plus 1, S minus 1, and then we have plus L plus 1. What else do we have? Then we have this right here, which is minus S minus 1 over 2. Okay. What do we have then? Then we have the expectation value of R to the S minus 1. So maybe let's go for plus expectation value of R to the S minus 1. Oh, this is supposed to be a square parenthesis. Doesn't matter much, but consistency. And this is multiplied by minus 2a, and down here by minus 2s over a s plus 1. And finally, we have the expectation values of R to the S. And there we have actually 2 times, right? We have 2 times n squared over a squared, right? We have 1 here, 1 here. I'm not hallucinating, am I? No, I don't think. Okay. And this is equal to 0. Great. So let's now move ahead and see what we can find. Okay, great. Well, now we can do some simplifications, but the thing is, we have in the denominators all of these s plus 1 and this 2. So maybe let's multiply all of this by s plus 1 and by 2. So if we do that, we're going to get a few different things. So this s plus 1 here, of course, will be gone. We will have 2 multiplying this, 2 multiplying this, and this will also be multiplied by s plus 1. In this case, this divided by 2 will be gone. I'm gonna maybe rewrite this, and then we have the s minus 1 that was already here times s plus 1. All right, and in this part, what do we get? Maybe I'm gonna take some more space. All right, yeah, I was being lazy. Let me take some more space. So this part right here stays the same. I'm gonna write this down here because space is getting tight and I don't want this to be too messy. All right, so when we multiply by 2 s plus 1, then the first term here will now be a 4 s plus 1, and this will be 4, but the s plus 1 in the denominator will be gone. So it's going to be minus 4s here. Okay, and then here, well, this is probably the simplest one. We will get plus, instead of 2, we will get 4 s plus 1. Okay. Now let's try to do some algebraic simplifications. So maybe let's begin with this. I'm gonna, just take it out. We don't have to work always inside this massive equation. So, you know, maybe let's call this, I don't know, x, and see what it is. So x is this thing right here. We can note that we can put these two terms together. So if we factor 2l, l plus 1, we get s minus 1 plus s plus 1. So the ones cancel out, right? This is considering this term and this term. And we get 2s. So we can actually write this as 4s times l. And then we have minus s, and this right there is simply s cubed minus 1. So we can factor out an s from all of this. So we are going to get s times 4l squared plus 4l multiplying through minus s squared plus 1. And here we can notice that we have actually a squared cube term. So we get s, my tablet lagged, s times 2l plus 1, right? We can factor this, 2l plus 1 squared, because this is, the first term is 4l squared, which is here. The second one is 4l, which is here. And the last one is 1 squared, which is right there, minus s squared. Okay, so we can rewrite this monster that we had up there in this much simpler form. So this is going to be s factor of 2l plus 1 squared minus s squared. Amazing. Amazing, amazing. I'm missing one parenthesis because of that. And here, what can we do? So let's now go for the next part. Well, what can we do to simplify this? Maybe let's call this y. So y would be minus 4 over a, right? That's the same in both. And then we have s plus 1 plus s. So basically minus 4 over a, 2s plus 1. So let's write that down. This right here is simply minus 4 over a, 2s plus 1. And there we don't really have to change anything. And well, in principle, this is already correct. All right, we are in principle done, but the way that the solution is given in the book is a bit different. So maybe let's try to accommodate that. So let's divide by 4 and multiply by a squared. Okay, so maybe let's do that. And if we do that, well, what do we get? We get this first part, which is going to be basically the same. And actually, I think that in the book, the order is different. So I'm going to switch the orders here. So let's begin with this. So r to the s. Now we divide it by 4. So this is going to be multiplied by s plus 1 divided by n squared, right? The 4 canceled out with this and the a squared canceled out. And now we do minus going to this term, right? So minus r to the s minus 1. And then we have this 4 which cancels out. And this a will cancel out this a partially. So we get a times 2s plus 1. And finally we have plus expectation value of r to the s minus 2. And this is going to be 4s over times, sorry, not over, but times, it's the other way around, right? It's s over 4, my bad, s over 4 times a squared. And then we have 2l plus 1 squared minus s squared. Well, and of course, all of this is equal to 0. I don't really have much space left in my screen. Well, equal to 0. And this is Kramer's relation. Let me now double check that I'm not lying to you. Let's go. So it's s plus 1 over n squared, s plus 1 over n squared. That one is correct. Minus 2s plus 1 times a, minus 2s plus 1 times a. That one is correct as well. And finally, it's supposed to be s over 4 times a squared, s over 4 times a squared times 2l plus 1 squared minus s squared. Yes, it is correct. Woo! This was intense, but let's just cool down and think of what we did. So the way we approached this problem is that we knew that we needed something that relates different powers of the expectation values of r to the s. So r to the s minus 1, and so on. And that's why we thought of the possibility of, since we're dealing with the hydrogen atom, this works exclusively for the hydrogen atom. At least what we showed is, maybe there's a different formula for other systems, but this one is for the hydrogen atom. So if we plug the u prime into what is the integral that we use to find expectation values, right? U r s u, that's the expectation value. Then we would get something with all of these terms that are dividing by r. So we would get a bigger integral that has different powers of r to the s, right? R to the s minus 1, and minus 2. That's why we did it. And then we were left, actually I might have erased that. We eventually found this right here, right? We found something that relates these expectation values, but to this integral that we didn't yet know, or we didn't know its value. And that's why we said, okay, let's take that integral, let's integrate by parts. And well, then we started. I think that I erased what we did there. But yeah, then we just went and integrated by parts over and over and over again. And to be honest, we didn't really do anything too crazy. It was just like annoying algebraically and a lot of integration. But yeah, that's this problem. I hope this was useful to you. If it was, well, make sure to leave a like on the video, maybe share with some of your classmates. That will really help me out. And if there's any particular topic or problem that you would like me to check out, leave it in the comments and I'll make sure to add it if I see enough interest in it. So thank you very much for watching. I'll see you in the next video. Thank you very much.